All right, so I'm probably one of the few who are not in the research field in this room, but get to use your research operationally. We kind of joke around that as meteorologists, we're mostly concerned about what falls out of the sky. And then once it's on the ground, we have hydrologists and other people that get to deal with it, right? Debris flows are one of those problem areas though, because we have to warn on them. So we do need to care about what is going on there. So let's get into it. I'm going to kind of take you on a day-to-day what we might be dealing with. So let's just picture this. It's a Monday morning, mid-July. It has been hot and dry, but suddenly there's a surge of moisture that's expected for the middle into the end of the week. What are we as meteorologists looking for at this point? So we're already kind of thinking about things. Do we have an environment that's going to be favorable for heavy rainfall? What are the antecedent conditions? Have there been any heavy rains recently? Are the soils wet or dry? We're also going to be looking at what is the precipitable water forecast to be. And just to show a quick answer, if I say precipitable water, does everyone know what I'm talking about? Yeah, mostly? Okay, good deal. I just want to make sure. And then we're also going to be looking at surface dew points. So precipitable water, general rule of thumb, we're looking at our forecast soundings and or actual upper air soundings from our office. We usually want to see the sweet spot, as we call it, of 0.6 to 0.8 inches of precipitable water. If it gets too high, we actually cloud over too quickly and we overconvect. And then we don't tend to get these heavy raining storms. As far as surface dew points, we're looking at dew points, generally you want them to be at least 50 degrees Fahrenheit or greater. If we have too dry of a surface layer, that rainfall evaporates before it comes in contact with the ground. We're also looking at what are the wind, temperature, dew point profiles within that cloud layer. So generally speaking, we're going to be looking at anything between about 700 to 300 millibars. So we're looking at that layer of the atmosphere where we're going to be seeing the clouds develop. We want to see light winds, right? Because if the storms are moving too quickly, they're not going to be dropping significant amounts of rainfall over the burn scar areas. We are wanting to see relatively small temperature and dew point depression. So we want to make sure that those profiles there are actually quite moist as well. And then we're also going to look at stability. How stable or unstable is the environment that we're dealing with? Obviously, we're going to be wanting it to be less stable to be able to get heavy raining thunderstorms. And then, are we analyzing any other sources of lift or forcing? And when I say that, I basically mean, is there a trigger? Are we going to have a cold front coming through? Is there a shortwave trough coming through? Is there something else that can help to initiate thunderstorm activity for us? Now, in terms of what are we going to start communicating at this point? So this is actually from one of our partner emails years ago. We actually have a little bit of a different format now, but I was trying to find some stuff that mentioned burn scars. And we're going to say, hey, there are increasing chances for thunderstorms. Our overall job is we want to help people make good decisions. I don't care how good of a forecast we put out. If action isn't taken, it means nothing, right? So right now we're just saying, hey, there's a chance for storms. Here are the highest chances. We're going to mention burn scars in the text because we want people to be alerted to that. We also might be showing you potential liquid totals. And of course, anybody who's dealt with thunderstorms knows that these precipitation totals can be incredibly variable. So results not guaranteed, but it at least gives a picture or an idea for our emergency managers and those in emergency services to deal with. And then we also have this thing called the freakout chart, also known as a threat matrix officially. But our office actually started this back in the winter of 16, 17, Any show of hands, who lived out in this general area in those years? It was a crazy winter. It was basically atmospheric river after atmospheric river. So we started this to start highlighting what areas of concern do we have. And again, here you can see flooding, we're highlighting, and we're talking about burn scars again, right? So this is just a general heads up. Now, as we get a little closer in, we're going to obviously be analyzing our satellite data. So here we can see a big swath of moisture moving into the west. The one that would be on your top right is showing a cluster of thunderstorms. If that's advancing northward, guess what? We're probably going to be having a busy day the next day. We're also looking at our forecast and/or current upper air soundings. Things like that. We launch weather balloons twice a day, every day out of our office. We also will look at observational maps. So on this, we're going to be able to plot what are our dew points, what are our winds doing, what kind of precipitation have we had in the last couple of days. And then there's this brand new tool that we like to use in the Weather Service. It's known as DESI, or the Dynamic Ensemble-Based Scenarios for IDSS. Yes, that is an acronym within an acronym. NOAA, National Organization for Advancement of Acronyms. But basically, IDSS is Integrated Decision Support Services. Now, we are using this tool because it is giving us basically taking hundreds of ensemble perturbations, all of these simulations, and giving us statistical analysis and ranges that we can use to then message to decision makers what might occur. So I can give you timing thresholds. I can tell you what our 1 hour precipitation rates might look like. That's a big indicator to say, hey, we might be having some pretty intense, heavy raining thunderstorms, right? I can tell you where the most likely scenarios for this will occur. But keep in mind, we are limited because this is model data, and I'm going to talk about the challenges as we go on. Things that we might be communicating at this point. We might put out a flash flood watch specifically for burn scars. Now, if you're looking at the date on this and thinking, well, that's weird, I didn't hear about that, that's because it didn't occur. So don't worry. I actually did this in what's known as our practice mode, and so I was making this warning up just for this scenario itself. So this is a watch talking about flash flooding on a particular burn scar and what are the risks associated. When we're putting out a watch, it means that we have at least 50% confidence that this will occur. But it's a good heads up for people. Other things you might see, we are very active on social media, both on Twitter, X, whatever the heck it's called nowadays, and Facebook as well. We're going to talk about, hey, flash flooding, here's the risks, burn scars in particular, be aware, pay attention to the warnings. We also might do messaging where we can take forecast simulation. So this looks like radar, right? If anyone's looked at weather radar, but it's actually a model-derived weather radar to give an idea of timing, initiation, where these storms might be and where the heaviest rain might fall. Some other messaging that we might end up doing here would be graphics like this, talking about flash flood risk on debris flows, talking about where and when we might be seeing the heaviest rainfall and what the peak hourly rainfall amounts could be. There are burn area flash flood threat matrices that can be put out. So we color code it based on how big of a risk particular burn scars are based off of all of the model scenario data that we have. Now let's say storms are ongoing. Well, we have all of the burn scars in our local area plotted up on maps. We can overlay then radar data right on top of it. We've developed programs so that all of our burn scar portable RAWs that are out there and any particular basically observations on the ground are feeding into this, and they can be watched as they come in real time, which generally is about a 15-minute increment, and we can see if any of them are starting to reach criterias as you go. We'll also be looking at MRMS data and flash data. We monitor all reports coming out of Caltrans, NDOT. Both of those are actually huge sources for us because we will start hearing about roadway problems pretty darn quickly off of any of those sites. We monitor social media channels, and we also watch cameras on the alert network, the alert wildfire network. Now you think, okay, those are meant for wildfires, but guess what? You can see storms pretty well too. Then they work great in the winter as well. There's also a bunch of research and new tools that are being developed. So this is a dashboard that is done through a GIS interface. It's called the SAFER, which for the life of me, I forget what that actually stands for because too many acronyms, but that's all right. Oh, situational awareness for emergency response is right on top of there. All right. But basically you're overlaying your burn scars, your hotspots, your radar. You can see precipitation rates. You can put all sorts of information right on top of there to keep an eye on what is going on in real time. Then here is another application that is also able to be used where you can look at real-time data coming in with burn scar monitoring and then also what you're anticipating for rainfall totals over the next hour as well. So just a few pieces of data that we get to look at. All right, so there's a real threat. We're watching this, we're monitoring radar. We know there are warm rain processes going on, and we see, and this is probably for all the weather nerds, which is not a huge percent of this audience from what I was seeing there, but low echo centroid below freezing level, all that means is that we have really heavy rainfall and it's not below freezing, okay? And so we notice that that's over a burn scar. Now what do we do? Okay, what are we looking at? We are, for some reason it's making me click like 3 times for the animations to go. All right, so we're looking, where is that cell over the burn scar? Is it brushing by? Is it directly over the burn scar? Is it a more sensitive basin? Is it a populated area? Is it in a super remote area that's going to flow into, say, wilderness area that's not as much of a concern? Right? We're going to be looking at a lot of these different factors. We're going to look at the instantaneous precipitation rate. So on radar, we're not only looking at overall liquid totals, we're looking at instantaneous rain estimates as well. So how rapidly is rain falling out of that storm? Is it lasting for one scan, right? We're getting scans generally 3.5 to 5 minutes, every 3.5 to 5 minutes coming into the office. So are we seeing it off of one and then it pulses down? Or is that storm keeping those high rates going for several scans? Which is then when you start to notice, okay, that's going to be a problem. Any nearby observations that we might have, you know what, those storms are pretty notorious for missing the bucket. We don't have a lot of observations out there, and my goodness, when we actually get it to hit, it's amazing. We also use this tool called FFMP, or Flash Flood Monitoring Prediction. I'm trying to, see, again, acronyms. But we can feed many different radar data, anything from legacy, dual pole, MRMS. All these different sources can be fed into it, and all that's really looking at is flash flood guidance for basins. So we take what the researchers are looking at, we're plugging that in, and we're looking at what has fallen derived from radar compared to what research has shown will trigger a flash flood or a debris flow. And then also we're looking at those hydrologic runoff models and satellite data as well. And I put a little itty bitty dual pole thing in there for anybody who wants to geek out on the details. Okay, so the actual process. We use this program called Hazard Services. This program is actually relatively new. We used to use a different program to put out warnings. So we've only been using Hazard Services for a couple years now. But we pull it up. We quite literally draw in our warning. We can overlay basins. We can do a lot of different things. We can say, hey, if this much rain is falling in this basin, where is that rain going to go? Based on the topography, based on what we know about it. And we can overlay all that. We draw it in. It pulls up this wonderful little, basically, entry box for us. We talk about how long we want that warning to be out for. We tell it the parameters. If it is a burn scar that we're concerned with, we enter what the burn scar name is so that it's calling it out specifically. We will specify if we know there are impacts. We will specify if it's radar derived. We'll basically put anything that we have information-wise straight into this warning. Then it pops out this lovely little text for us, which then we can edit, and it gives you the basics of the what, where, when, and all of that so that you know what to do. If we are looking at amounts that say are only slightly over thresholds, right, we have guidance, again, based on research, saying how much is going to trigger a flood or a debris flow. If it's only slightly above, or if we are in a remote or not as sensitive part of the burn, we're probably going to issue an advisory, not a warning. If we are in a very heavily used area, campground, big hiking trail, things of that nature, you know it's going to flow across a roadway, or we have widespread heavy rainfall amounts that are well above our thresholds, that is when we'll issue a warning. Now, when it comes to warnings, we actually have 3 different tags, if you will. So we have a base tag, which is you can find trouble. Considerable, trouble is going to find you, or catastrophic, trouble is here and it's bad, okay? The second 2 will actually WEA, or wireless emergency alert. Those are the ones that go off on your phone unless you go in there and tell your phone, I don't want them. I don't recommend turning it off. Keep that thing on. If it's going off, there's a reason for it. So with the base tag, it's generally isolated to vulnerable locations. Most of the warnings you're going to get are going to have a base tag on them. They're not going to be incredibly impactful. If we are looking, again, incredibly heavy amounts of rainfall over an area that's more sensitive, we're probably going to go considerable. We want that to WEA. We want that to trigger on EAS. Now, the catastrophic is your flash flood emergency. Okay, this is like Montecito. So that's going to be saved for the worst of the worst. And we're not going to be putting those out very lightly. Here's an example comparing a considerable tag to a catastrophic tag. And you can see that one says warning, one says emergency. And one has the dangerous, one says extremely dangerous. Just a few adjectives, but just trying to hammer home the point that one is basically, it's going to come for you. You want to make sure you are out of harm's way. And then here's another way to kind of think about the differences between an emergency and a warning. Again, emergency, incredibly rare. Severe, life-threatening, catastrophic damage. Regular warning, it's happening or will happen soon. Still bad, still take cover, but not as serious. And then in terms of social media messaging, flood advisory, we basically just kind of break it out. Say, hey, moderate risk, this is what it means, debris flow is possible, here's where you need to worry about it. For the warning, in this case, more of a major risk, we would go extreme if we were talking emergency, and we highlight the areas and talk about the problems that we're going to be having. So some of the challenges that we get to deal with. This is just showing the burn scars in the last 5 years, right? That's a lot of area that's covered. Each one of these has its own specific criteria. Each one of these has to be monitored. And kind of breaking it out here, this is an example from our Tamarack fire, but showing how many sensitive areas there were. How many specific basins can cause these catastrophic debris flows that are going to be property threatening, that are going to be life threatening. It's a lot of little things to focus on. Now, mind you, when we're looking at this, we have all the burn scars, but these are not the only things that the radar operators are watching, right? We also have to watch, do we have any outflows that are bringing significant wind to any locations? Is there a haboob? And when I say haboob, do you guys know what I'm talking about? big wall of dust, basically, like a big dust storm, that is going to close down an interstate and cause hundreds of accidents? Are there areas that are getting pelted by hail and crops that are getting damaged? How about aviation? How about the airports that are calling us? How about the ongoing other wildfires that the firefighters need to get to safety? We are juggling an enormous amount of things as we're watching this, in addition to trying to figure out every little basin on that burn scar. And not just one burn scar, but sometimes upwards of 20 burn scars in our local area. So this is really high stakes situations, but we're dealing with imperfect data. So before an event, we might have conflicting scenarios and data that we're dealing with, right? We look at a lot of the ensemble simulations. We can sometimes have them not line up. I know it's shocking that forecast models are ever wrong, but they are. But when we're doing that, what do we believe? And that's, again, where looking at our probabilistic scenarios is coming into play. Being able to trust new forecast data. We've had a lot of advancements in the science over the past, let's just say, decade. I've been doing this about 20 years now, and I've seen a lot in the last 20 years, and really more so in the last 5 to 10. We have new data coming in. We have data coming in that we don't always believe, and part of that is climate change. I'm going to give you an off-wildfire example, but we had atmospheric river in 2021 in October. That came into the west. It was the strongest October atmospheric river to make landfall in 40 years. The forecast scenarios for the amount of rain into Reno were totaling, in 2 days, the same amount that we had gotten the entire water year prior. Okay? And all of us were sitting there going, what? No. Another example would be the Pacific Northwest heat wave. Remember when Portland hit 116? I think it was 116. Everyone again, the model's broken. Guess what? It wasn't. It happened. So we're trying to trust this new data. We're trying to reframe our brains. We're trying to think about, as meteorologists, what we know and then what has changed and what is changing. We also know that models do not forecast pulse thunderstorms well. Around here, pulse thunderstorms are life in the summertime. That is predominantly what we deal with. So pulse thunderstorms, storm pulses up, it rains out, it outflows, it's done. Okay, these are really short life cycle storms, generally on the order of 15 to 30 minutes at most. Now, when those collapse, they can send out outflows, which then can initiate new thunderstorm activity. So, do you think the model knows where the storm was to begin with? No. Do you think that storm then that is now dissipating, do you think the model's going to be able to forecast that next one that it didn't even know the first one existed? No. So models do not handle it well. We want to make sure that our public and public safety partners are educated on the risks and even more so believe you. Okay? With our partners, we have really good relationship with emergency management and other people who are out in the field. That's actually part of what I do. And Tim, our hydrologist back there, he does a lot of it as well with our office. And so they believe us. They trust us. We have great relationships. How about the general public when you tell them, you know what, you might be having a big mud flow coming down the side of the canyon next to you. If they've been here a while and they've seen it, they start to believe it. But some people come in new and they say, oh, you guys don't know what you're talking about, until it happens and it's too late. Properly communicating the risk. I think I already said this, but I don't care how good of a forecast we give. If we cannot communicate it and people do not take action, it makes no difference. And then I mentioned those p-watts being too high, the precipitable water. If it's too high, we actually cloud over. So a day that looks really good may cloud over, and then you're done. You're capped. You're not getting those storms forming. So during the event, things are changing faster than we can get data, right? These storms are popping up, they're pulsing, we're looking for ground truth. We're sometimes not getting it until it's too late. We also are trying to discern, is this a nuisance event or is this a high impact one? Are those really high instantaneous precipitation rates going to continue, or are they going to pulse up and pulse down? Radar limitations. Anybody who's worked with radar data in the West knows that there are mountains. Mountains block radar beams. We don't play well together. We don't get to see the storms that are going on. So we have a lot of challenges with getting proper radar data. Plus, radars are spaced very far apart. So you're not always getting a good sampling of the storm. Storms not hitting the bucket. Great example. So Reno, probably our most well-sampled area in the entire area that we cover. We had a storm a week ago. On MRMS, it was showing 2+ inches in a very localized area in southeast Reno. With all of the gauges around, not a single one captured it. Now picture these storms out over remote terrain. We're not getting data, and we're definitely not getting it fast enough. Other problems is we get some bogus reports from the public. People will tell us, oh my God, it's flooding. And then you find out that it's a culvert that's blocked and there's just like a couple inches of water and it's not even running down the hillside or doing anything, right? So we have to kind of discern, okay, is this a real report or is it not? Not wanting to cry wolf and have too many false alarms. We have to be incredibly sensitive to these burn scar warnings, but we also don't want to do it too often. Because if you start crying wolf, you start telling people there's going to be a slide and then nothing happens, people stop believing you. Knowing that each burn and each storm can produce differing results. We have seen very similar looking storms with very similar looking rain rates. One produces a flow, the other one doesn't. How do we discern which is which? Hint, hint, researchers, help us. And then the instantaneous rates, are they isolated or are they continuous? So as far as workload challenges, it's tiring. You have an increased risk for rapid onset. As I said, we're monitoring a ton of things ongoing at the same time. So it's more strain for the forecasters. And this data can go on, it can go on for years too. We have to educate the public and partners on our new risks. The burn scars are going to be in terrain with very limited observational data. Warning fatigue. So people were getting all kinds of warnings when there were fires ongoing, and then now there's floods ongoing behind it. They're tired. They're like, oh great, my phone's making more noise at me again. Yeah, what do I have to worry about? So again, getting to the public and making sure they know. Pop-up convection. We have seen storms literally pulse up right on top of a burn scar. So it's not like you get to say, oh, there's a storm, let me track it and watch it as it goes. Nope, that thing just pops up, forms right over the top, and is it gonna stay there or is it gonna collapse? That's you don't have a lot of time to make that decision. And then, is the public going to respond to a watch or wait for a warning? Mind you, the warnings can have little to no lead time on them. All right, let's do a little case study here. So we're gonna look at the Slinkered burn. So this was up off of US 395, if you know where Topaz Lake is, right near that area. This occurred on May 21st in 2018. I was actually working this evening. There was a decaying thunderstorm approaching this burn scar, right? So we're keeping a close eye on it, but it looked like it was dropping off. The instantaneous rainfall rates right over the scar were only 0.2 of an inch up to 1/2 inch an hour. Mind you, they were stronger than that as they approached the burn, but once it got over the burn, that's what we were looking at. And here's kind of a picture. So you see that red outline, that's the burn. The green is showing where those higher rates of rainfall were. And then you notice that they're not really over the burn scar. So the heaviest rates eased, but they were just high enough. We actually had a portable RAWS that was out there, and it reported 0.26 of an inch in 15 minutes. And mind you, 1/4 inch in 15 minutes was the median threshold for issuing a warning. So warning was prepared, but as it was getting prepared, there was a report of 2 feet of mud and debris closing 395. It was that fast. Luckily, nobody was hurt in any of this. So here's kind of a close-up of the basin. You can see which two basins slid. You can see Topaz Lake and 395, where the post-fire RAWS was. And kind of the likelihood here was a 40 to 60% likelihood that a 1/4 inch in 15 minutes would cause a flow. Here is looking at the actual instantaneous, or sorry, the 15-minute intensity coming up here. And you'll note the modeled threshold, so that's the median threshold being met, and the debris flow really occurred within 10 to 15 minutes. So we really had no data until it actually happened. And the intensity of this event was much, much higher than any other previous winter event, despite the fact that we had significantly higher rainfall totals on that burn over and over and over again during the wintertime. Then, July, same year, we had another flow, this time on the 89 side in Alpine County. Closed 89 for about 24 hours. You can kind of zoom in here, and again, looking at the burn, you can see where the second debris flow occurred. Similar, actually this one's a 20 to 40% chance for the rainfall, but in this case, radar, you could see that it had those high rates right on top of the burn scar. So this one, the warning did go out for, and it did verify. Now, if we do not have specific guidance, this is kind of what we use for our initial guidance. Just a general rule, timber fire and steep terrain, we're looking at 1/1500ths of an inch in 15 minutes. It's not very much rain, right? It's pretty small amounts. And then we also have 30 and 60-minute criterias, and then grass and brush and steep terrain. It changes it and bumps it up just a little bit. There are also a lot of post-fire RAWs that are getting installed on burn scars in California and Nevada thanks to grants and partnerships. I got Tim in one of those photos. He's in the back there. Tim, if you want to wave. Sorry not to call you out. But he is great with working with our partners and getting these things installed. Hopefully, we actually then can sample what's going on those burn scars. So something to point out here, we have differing geography and differing impacts. So when we have, say, pulse storms, which we have around here, they pulse up, they pulse down, then they're done. If we have other parts of the country, they might have much more groupings ongoing here. I'm just going to go through the rest here really quickly for this. Wintertime risks. Montecito, everyone's probably very familiar here, but this was a NCFR, narrow cold frontal rain band, that caused the heavy precipitation rates. And even though an atmospheric river brought tons of rain to the area, it was actually that NCFR and the heavy rates that triggered the debris flow. So the key takeaways here, it's those short duration, high intensity rainfall events that are the main trigger. The instantaneous and 15-minute rates from radar are much more important than the storm total and 1 hour products for us to look at. Long duration events with medium intensity tend not to trigger debris flows for us. Moist soils are not an important trigger, but does factor into the speed and volume of the debris flow. And the timing of the warnings are really going to vary depending on geography and local weather patterns. With that, are there any questions?